All right, so what I'm going to talk about is some of the advanced node effects that we have seen in the advanced technologies, and how at GlobalFoundries we provide solutions to customers for these issues. Okay, so let me start with just introducing you to our advanced node products. So in the 28 nanometer space, we have a high performance 28 HPP targeted at high performance computing and network applications. And then for low power, we've got two solutions, 28 SLP, also high K metal gate, and a polysilicon process, 28 LPS. Our 20 nanometer process goes extends the whole range from a low power variant all the way to high performance. And we also have 14 nanometer FinFET process. Okay, so the purpose of this talk is to kind of explain from the design community what are the challenges you're going to encounter as you go to design in these advanced nodes. So at 28 nanometer, we see a lot of layout-dependent effects. The best way to describe this is it's when you draw the transistor, the behavior of the transistor is not just a function of that particular layout. It's also a function of what's in the periphery. And we need a way to model that and plan for that in the design. We also have at 20 nanometer double patterning effects that impacts every aspect of the design, and I'll go into a little more detail on that. And then finally at 14 nanometer there's FinFETs. And so FinFETs bring a lot of new capability, but they also bring a lot of constraints and restrictions that all have to be factored into the design phase. So let me first talk about double patterning. So double patterning, it's written there, it's the process of decomposing a single design into two different masks. So what we're doing is we take a single device layer, we split it into two masks, and by doing that, we essentially double the pitch that we can achieve with lithography. But this brings a lot of challenges, okay? So one is it impacts our layout methodologies and complexity. So you need to use special tools. Those tools need to be color aware. You're going to find you're going to have to color different. We use color to distinguish between mask 1 and mask 2 on the same design layer. So there's a requirement on the designer in the analog world to be aware of the colors. This also, because we now have two masks for one layer, introduces a new source of variation in parasitic extraction. And this is sort of shown here with the two masks. So I have a blue mask and a red mask, but inevitably, because it's two different masks, there's going to be a relative shift from one to the other. And this is something that's a new source of variation in parasitic extraction that needs to be factored in during sign-off with corners. There's new constraints on metal fill. So historically, we've looked at fill as something where we had to achieve a certain density. Now we also have to achieve a certain color balance with the fill. It requires color-aware GDS2 and DRC, and also in the place and route flows, see significant enhancements where we require odd cycle fixing to be built into the place and route flow. And this is a must-have to be successful at 20 nanometer. The odd cycle is shown here on the right. The definition of an odd cycle in GlobalFoundries terms is that if you have an odd number of shapes, there's no way to achieve a decomposition to achieve the rules. And you can sort of see it here. I have two greens in close proximity. I have two choices to fix this. I either have an even number of shapes where I have a red in between these two, or else I have to space them a little further apart. Okay. And this is what auto-fixing is about in the place and route flows. Another issue that I highlighted at the 28 nanometers, where we initially saw it, is layout-dependent effects. So layout-dependent effects are caused by, there's a couple of things here, but I'll highlight first the dual stress liner, which is a technology that adds a compressive force on the PMOS and a tensile force on the NMOS. And this has the effect of increasing the performance of the transistor. So stress is good, okay? So it's a good thing. We want stress. But designers want to be able to predict it at the schematic level. And one of the challenges we have is that over here, the proximity of the transistor to the N-well boundary has an impact on the amount of stress that on the amount of stress that you're actually going to see in practice. So in this case, this transistor, because it's further away from the boundary, is going to have less stress than this one, which is close to the boundary. And one of the most significant challenges in analog design is attempting to make sure that the performance of the chip after you simulate this at the schematic level is close enough to what you're going to see in post-layout extraction. And so here what we have to do is to try to help the designer have a good way of estimating this effect early on in the design phase. Okay. And to do that, we've worked very closely with Cadence to develop what we call layout-aware design flow. So there's 3 components to this. So at GlobalFoundries, we have this standalone script that allows you to calculate the impact of stress on the transistor. It's not built into the device model, so you don't have to do simulation. And the value of this is that at the schematic level, we have a way to estimate the impact of stress and show it to the designer in the schematic. It's also integrated into Cadence's Virtuoso LDE layout analysis, so in real time, the layout engineer can track the constraints from the designer and make sure he's not exceeding them. And then, of course, for full accurate post-extraction, the same capability is built in there, so you get a fully accurate model of the behavior of the transistor. So I've described to you, some of the challenges. I guess what I want to talk about next is, how do we deliver this to you? How do we give you this information? And so what we do at GlobalFoundries is we develop what we call reference flows. And this is an example of our analog mixed signal design flow. And it's a design flow it's a set of reference methodologies built around a reference design. And so here in this case, what we have is for analog mixed signal, we implemented a real chip. And then in the process of implementing that chip, we captured all the learning into different modules. So you, the user, can run each of these modules standalone to learn about some specific topic. So in functional design, we talk about which corners to use, Monte Carlo simulation, how to use the LDE models to estimate layout-dependent effects. There's also a double patterning aware custom layout flow, again, where we highlight the use of Virtuoso 12.1 in order to be able to efficiently perform double patterning aware layout. In our post-layout design validation, we give detailed scripts, demonstrate how to do R only, C only, OA and back annotation. All of this is enabled and demonstrated in a sort of out-of-the-box fashion that you can use with our PDK. And then physical verification and decomposition, where we provide guidelines of how to solve color problems. And there'll always be color problems at the end, typically around large capacitor arrays, sort of large uniform structures. The tools are pretty good at solving most of the issues. So this is, you download from GlobalFoundries a reference design, all the scripts, the database, documentation. This is maintained at GlobalFoundries. We maintain it. We keep it up to date with the PDK. Okay. By the same token, we also have RTL to GDS2 flows. And, in this case, I would highlight that, particularly at 14 and 20, there's significant PPA scaling advantages. And what we've observed is you cannot get those unless you take full advantage of some of the new capabilities in the tools. And those are demonstrated in this flow. We work very closely with all the EDA vendors. In this case, I'm highlighting Cadence. But we've worked carefully with all the EDA vendors to make sure that their tools work with our PDKs. We've designed real chips to QA the overall flow, PDK, and IP. But in this case, what we're giving you is a sort of a small open source design that again works out of the box and can be used to quickly set up the PDK environment, set up the flows, and it's a means for us to deliver methodology to the customer. So embedded in this are design guidelines, recommendations, how to do double patterning aware extraction. I talked earlier about the challenge with the variation. So we embed solutions here. We explain how we come up with those solutions and why you should use them. Okay. Also in these flows, we deliver design guidelines. And these design guidelines will provide margin recommendations, the temperature impact of the sign-off choices. Power mesh design. There's a whole host of guidelines provided along with these flows. So then, if I kind of summarize on the enablement front, there's three things we're doing here. So one is we're fully QAing the EDA flows with GlobalFoundries PDK and our open source and silicon validated IP. Okay. The second thing is we provide packaged and downloadable flows and documentation for RTL GDS2 as well as analog mixed signal. So these the customer can download, you can install them, you install it with our PDK, and then you have an entire flow. And then the third one is design guidelines and GlobalFoundries tested methodologies that demonstrate solutions for the key technical challenges. All of this is available for download.